Okay, everybody. We're going to continue what we were talking about with our electron configurations. Just a little quick review here. If I put this slide up from where we were doing before, when we talk about electron configuration, I'll put up the first 10 elements here that we've done in our notes. Just to really review, is you have a situation where we have our nucleus down here, right, like I said. And then what we do is we start off with the first element, hydrogen, being a 1s of 1, 1s1, then 1s2, and then we go to 2s1, 2s2, and then we begin to fill the p level. Okay, so again, the energy follows this way. We're going to go from 1s to 2s to 2s to 2p. When we finish the 2p, we go to 3s, and when we finish the 3s, we go to 3p, and so on. Okay, so that's really the pattern that we're going to see here. Now, if you go up to the table, you'll see it's the same thing. 1s1, and then we finish 1s2. Okay, now interestingly enough, the row number here is the first energy level. So when we finish the 1s1, 1s2, we finish the first two elements with helium. When we go into the second row, that starts the next energy level with 2. We start with the 2s2, and then we go to the 2p6, 1, 2, 3, 4, and 5, and 6, and then we would be with neon down here, 2p6. So as we go across the periodic table, we'll see there's 2s2, so this would be s2 level. This would be s2, this would be s1, s2. And then if you notice that there's actually 6 elements long here for p1, p2, p3, p4, p5, and p6. So neon would end here with neon. All right, so if you notice there's 4 real sections to the periodic table here. There's the S block. This is called the S block. This is the P block. This is the D block, and this is the F block down here. Okay, now interestingly enough, S only holds 2 electrons. You'll see each S level going up from the nucleus, each energy level, holds 2 electrons. So you would only be 2 elements wide here. Okay, the P block, which holds 6, you can see anytime you have a P, it only holds the 6. That would be 6 elements long here. And when you finally go to the D, that would be 5 elements. Oh, so I'm sorry, 5 boxes, or times 2 electrons would be 10 elements. The D level is 10. Okay, and the F, of course, would be 7 times 2 is 14. So it gets a little more involved as you go up. But the key is you can figure out all of this from the periodic table without memorizing all this. So everything sounds real good, right? We have 1s2, then we have 2s2, and a 2p6, 3s2, and 3p6. Now, the problem starts, just when you think you have everything okay here, going away from the atom, what we find is something very interesting. As you go away from the nucleus, okay, when you finish the 3p6, so 3s2 would be here. So you start the third energy level with 3s1, 3s2, okay? Then you go 3p1, 2, 3, 4, 5, and 6. Once you finish 3p6 here at argon, and you should remember that every time you fill a p level, we're going to be finishing a noble gas. So again, p6s will always be noble gases, and that's one of the reasons why they're stable, because you always fill an S and a P. Now, something interesting happens. You would expect, and I repeat, you would expect to go from 3S to 3P to 3D. However, there's a break in the pattern. All right, if you notice the level of this, and again, as you go up in energy, electrons want to be as lower energy as possible. Remember, the nucleus is down here. What electrons want to always do is they always want to go to lower energy first. So if you compare the 4s level to the 3D, we're going to find that electrons are more stable if they don't go to the 3D, but they actually go to the 4s first, before the 3D. All right, now I know that seems to be out of order, but there's something important that you need to know about the S level. The S level actually goes and gets closer to the nucleus on average. The cloud is actually closer to the nucleus, so slightly more than the 3D. So that means it's lower in energy, and because it's lower in energy, elements will normally go to the 4s1, 4s2 first. And you can see that in the table. You'll see here that you go to 4s1, then 4s2, and then you're going to go back and start filling here with 3D1. Okay, so it's really important that you understand that after 3p6, you go to 4s and then 3d. Okay, because of the lower energy. So if you just follow this thing going on through here, if you just follow through here, you're going from 4s down to 3d. Okay, and then you're going to follow 4p. So if you follow the periodic table the way it goes, you'll be going from 4s to 3d to 4p to 5s to 4d. So here the D level is 1 energy level behind. Okay, so that's important to know. The D level is at 1 energy level behind. All right, so that's really important. So again, that's how we'll do it. So if we go forward to the next bit of notes here, and then we look at the filling the D levels are unique. All right, because they're 1 energy level behind. So after the third energy level, S levels fill before the D because they're initial lower in energy. Okay, so if you look at the first element, calcium, okay, calcium is going to be 4s1, and then calcium would be 4s2. Okay, if you look at it. And then the scandium will be the first transition element at 3D. Okay, so scandium comes at 3D1. All right, so scandium will begin to fill the 3D1. Now remember, you're going to fill one element at a time here. All right, so the key point is this, is what you want to remember. As the D fills, the S electrons end up becoming higher in energy, and they'll switch, okay, and are lost first when the atom reacts. We'll get to this a little bit later. So write the electron configuration for vanadium. Vanadium is going to be atomic number 23. All right? So we can do that. So if we pause this a little bit, and I can go back, I come out of this and I bring this up, okay, and we use this, we can see here that if you're doing 23 electrons, you can look at the table here and say, okay, 23, so that would be 1s2. In fact, we can do it this way, it'll be easier. If you're following along with your table. Vanadium would be atomic number 23. So it would be 1s2, 2s2, 2p6, 3s2, 2p6, 3s2, 3s2, sorry. So 2p6, 3s2, 3p6. Now that would be 18, right? 2, 4, 6, okay? And this would be 18, okay? And what we're going to do is we're going to fill the 4s2 first to make that 20, okay? And now we need 3 more. So what we're going to do is use the D level. So we're going to go 3D, okay? And we're going to have 3D3. Okay, so that would be the configuration of vanadium, because vanadium is going to have those extras. Now, one thing to note is if I was to draw the boxes for this, okay, just remember when you do boxes, in this case, we're going to have 5 boxes for D, and what we're going to do is we're going to fill one at a time. 1, 2, 3, like that, and then go back and fill them in. So again, these are all filled. These are all filled, all right? So that's the key. You're going to fill 4S before 3D. All right. Now that's one thing you want to remember. And then now there's actually exceptions to this even. All right. So if we check out the transition elements, and these are the transition elements in the D level. All right. So if you start with scandium, scandium is going to be 4s2, 3d1, then 3d2. Vanadium is 3d3. So we're going across the first row of the Ds. Okay. Chromium is 3d5. Now, what you would expect, okay, in manganese, okay, or chromium. In fact, when you go to vanadium and you go to the next thing, what you would expect is 3D 4s2, right? That's what I would expect after this. So chromium, I would expect this to be the case, right? But the problem is, if you look at 3D4, if you look at 3D4, okay, here's 5 boxes and 4s2, that would be filled there. If you look at 3D4, what we find is there's an empty box in here. So what chromium does is chromium kind of messes up the pattern. What chromium does is takes one of its 4s2 electrons and moves it into here, fills that one, and has one in each box. So it ends up making not 3d4 4s2, but 3d5 4s1. Okay, and that becomes stable. So you can see how in chromium here, it's not the next step. It actually takes one out of the 4s to make them all even. All right? So we're going to wait on that a little bit. We're going to circle that one and say, okay, that's a little different. All right, now we continue the pattern, right? We go 4s2, 3d5 manganese, then 3d6, 3d7, 3d8, okay? And then when we get to copper, again, we're expecting in copper to be 3d9 4s2. But again, there's a problem with this because if you take 3d9, if you take our 5 boxes again, and my 4s2, if we look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have an empty space there. And this is 4s2. So what copper is going to do is it's going to come here and it's going to fill that in to make 3d10 4s1. Okay. Now, filling this makes that stable. Okay, because it's completely stable. And making sure these guys up here are half filled is also stable. So there's something unique about chromium and copper. The fact that copper has a fully filled D and that chromium has a half filled D tells us something that these could be stable because fully filled and half filled are actually stable. Okay, and a little bit about chromium too is the fact that this moves into here is probably because these two electrons are repelling each other. So you repel this electron into the empty box. All right? So, and then you continue and you finish up everything with zinc with 3d10 4s2, which is the last D electron of that group. All right? So that's an important thing to know about that. All right? So some rules that you want to be aware of. Your elements with half-filled orbitals, okay, can minimize repulsive forces. Okay, again, electrons don't want to be next to another, okay, which is going to increase their stability. All right, again, the more you separate electrons, the more stable it becomes. Okay, and atoms or ions with filled energy levels are also most stable. So when you have filled energy level or filled boxes, you're going to be very stable when that happens. Okay, and what I mean by the repulsive forces is, again, if I show you one more example, if I have 3d4, okay, like this in chromium, right, and I have a 4s2, all right, these are going to be repelling, right? They'll repel. So what happens is they'll repel each other apart, and it will push this extra electron into that box. So then you have 3d5, 4s1, okay, which is what chromium does. All right, so to repeat, half-filled are stable, okay, and fully filled are stable. All right, so that's what you want to get out of this exceptions. All right, from here on in, it's just going to be a little bit easier because then we can just see what else we can do with electron configurations, okay? And that's sometimes writing shortcuts. We know that these can get quite long, right? These electron configurations can get very long. So what we're going to do is we're going to find the previous noble gas. And what's great about the previous noble gas is the previous noble gas we know is filled. So because of that, we can use that as a shortcut and then add the remaining electrons. All right, so that's what we're going to do. We're going to use the previous noble gas to that element, and we're going to add the remaining electrons. All right, so for example, if we want to write the electron configuration of phosphorus, we would write 1s2, 2s2, 2p6, 3s2, and 3p3. All right, now if we write that for phosphorus, that's correct. However, you're getting kind of long here. If we look at this part of the configuration, all right, and I look at that configuration, I'm going to find that that is the same configuration as neon. If you look at the table, you'll see neon is 1s2, 2s2, 2p6. And what's great about neon is that all the boxes here are all filled. Okay, these all are filled. So if that's filled already, we can represent this part of the phosphorus configuration as neon in parentheses, and then add your remaining electrons. Okay, so phosphorus is really neon plus the extra 5 electrons, right? Because neon is 10. So what you want to do is neon is behind phosphorus in the periodic table. So again, that's why you want to find the previous noble gas to wherever you are on the table. All right, and that would be neon, and then we can count up and add the remaining 5 electrons, 3s2, 3p3. All right. Another example of this is if you want to look at bromine. Bromine would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we count 5 more to make 35. And again, this is a long configuration. So what we want to do is if we look behind bromine, the previous noble gas in the periodic table to bromine, if you count backwards, all right, is going to become argon. And argon is this guy. Okay. All right. So argon's configuration is up to the p6, right? And since that's argon, I simply add the remaining electrons to this. Okay? And that becomes the shortcut of writing a configuration. All right? So let's just say I wanted to write the shortcut configuration for zinc, 30 electrons. I would go 1s2, 2s2, 2p6, 3s2, 3p6. I got to go to 4s2. I got to go to 3d10. Remember, S before D. And when I'm finished with D, okay, I'm done. Okay, so I'm done with this. Now this finishes zinc. Okay, zinc finishes the 3d10 4s2. All right. So now what we can do is we can look at the previous noble gas here, which would be argon. Right. So we can say the shortcut for zinc is argon 4s2 3d10. Now, you can also write this, or you can put the 3d10 beforehand. So you can do that. You can do this as 3d10 and 4s2. That's also possible to do. That's okay if you do that. All right. If you wanted to do for iron, okay, iron, again, you can do the same thing. We can go 1s2. And again, iron is going to be Fe. That's going to be 26 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. Again, we got to go 4s2. Okay? And then we have to count up to 3d6, and that would be iron. And again, what's our previous noble gas? The noble gas that comes before iron is argon. So we could say argon 4s2 3d6. Or you can switch the two, however you want to write it. All right, so that's the key. That's the basic idea between shortcuts in that way. All right? All right, so I'm going to stop here. These are the first two things. Again, you want to think about the D level and the S level and be able to write your shortcuts. Okay, definitely ask some questions. Write down your questions and feel free to come in and ask me. Okay? And we'll continue later on. Thanks, bye.